Coach Travis here with another calculus video. So we got a problem here. What does it say? So we got a particle is moving around and the velocity of the particle is given by this logarithm function. And okay, the particle is moving on a certain interval of time from 2 seconds to 9 seconds. And we want to know what's the total distance. So what is the total distance that's traveled by that particle? So this is one of those questions where we know the velocity. So we're told the velocity of the particle, but then we need to translate that velocity into a total distance. So again, I love problems like this. It's like if you think about if you have your cruise control stuck on a certain velocity, then it's easy to find how far you go because you're just traveling at a constant velocity. And distance is just velocity multiplied by time. So if your velocity is constant, then finding the distance traveled is an easy problem. But what makes this a neat calculus problem is, well, what if your velocity isn't constant? So you don't have your cruise control set. So your velocity is constantly changing. How the heck are you going to find distance in that sense? Because you can't just do distance times time because sorry, I said the wrong thing. You can't just do velocity multiplied by time to get distance because the velocity is not constant. So anyway, that's probably enough rambling about that. So how do we do problems like this? So this is a job for what we call the net change theorem. So the net change theorem was this. It says that, okay, if you know the derivative of some function, so little f is a derivative of big F. Then the total change or the net change of big F, I guess it's net change, not total change. The net change of big F over some interval is the integral of that derivative function. And so that's useful in our particular problem because remember that velocity is the derivative of position. So if I want to find the net change in position, if I want to find the net change in position, I need to do the integral of the velocity function. I think that's the setup we need here. So basically that's what I could say here. I could say, okay, what this question is, thanks to the net change theorem, what this question is asking me to do is we could say it's asking me to find the integral from 2 to 9 of, let's see, and I'll make this dt. And then inside, I'm going to have the velocity function, which is 3 times the log base 3 of t plus 4. Okay, but there is a catch. So you have to be a little bit careful. That I'm lying to you a little bit here. Wait, I'm not lying. I guess I haven't lied to you yet. What's happening here is this, the net change theorem says that this integral is going to tell us the net change in position for this particle that's moving around. And so if you have a keen eye, you will say, well, wait, Travis, the question's not asking us for the net change in position, it's asking us for the total distance that's traveled. And that's slightly different, right? Because, for example, like if I have a particle that starts here and then it moves way out here, but then it turns around and moves back and stops right there, then the net change is just that distance right there. Whereas the total distance is sort of the length of this, how far we went in the positive direction plus how far we went in the negative direction. So this particle traveled a lot farther than its net change might indicate. So if you have a keen eye, then you would say, wait, Travis, I think you've got the wrong thing here. What we really should have here is we should have absolute values. And that is, if you thought that, yeah, you're absolutely right. That the absolute value, if you find the integral of the absolute value of the velocity function, then that's what gives you the total distance. So it's kind of a subtle difference between net change and total distance, but we've talked about that before. So okay, so what we have to do basically is we have to evaluate this integral, because if you want to find total distance, then the net change theorem says that the total distance traveled is the integral of the velocity function. Okay, and so now I've got good news. Now that I've just said how important it was to have those absolute values there, I'm going to say that we can ditch the absolute values, because think about what does an absolute value do? An absolute value, it leaves positive numbers alone, but it changes negative numbers into positive numbers. But let's think about this logarithm. I mean, this logarithm we're looking at here is log base 3 of t plus 4. And I'm going to leave a blank for the t. Because let's think about what is the value of this function going to be on the interval from 2 to 9. So if I put a 2 in here, I get log base 3 of 6. And if you think about it, that's a positive number. And likewise, if I think, well, what's log base 3 of 9 plus 4? Well, that's also, because I'm putting in 9 because that's the upper limit. That's also a positive number. So the moral is this logarithm is always positively valued on this interval. So those absolute values are not necessary, well, theoretically they're necessary, but in practice they don't change anything. So we might as well just make our life easier in this problem by getting rid of them. So, and let me say that again to make sure it's clear. Usually, you can't always do this, so you have to be careful. You have to check before you just throw away the absolute values. You have to check to make sure your function is always positive. So if your function is always positive, then it is safe to get rid of those absolute values. Basically what that's saying, essentially what's happening physically in this situation is that the particle is always moving in the positive direction. This particle is never turning around. It's just always moving to the right. So the fact that it's never turning around means that we don't have to worry about the absolute value, because the net change, if it's always moving in one direction, then the net change is going to be the same as the total distance, because it never turns around. So okay. So now we have to evaluate that integral. Oh brother, so how are we going to do that? Okay, well, so let's see here. So this is kind of a complicated thing. So I'm going to do this with u substitution. So I'm going to look at this and I say, okay, it kind of has an inside and an outside function. So like the inside function is t plus 4. So I'm going to set u equal to t plus 4. And so then, okay, so then my integral is going to turn into the integral from 2 to 9 of 3 times the log base 3 of u and then dt. So there's a u. So that t plus 4 turned into a u. And now this is not a good thing because it has u's and t's mixed together. I only like to have one. I only like to have one variable. So, like we usually do with u substitution, now we need to figure out how to get rid of the how to get rid of the dt and turn it into a du. So, all right. So over here, I can find the derivative of both sides with respect to t. So on the left-hand side, the derivative is du dt, and the right-hand side, it actually just turns out to be 1. And then if I multiply both sides by dt, I get du is equal to dt. Okay, so this is one of those rare occasions. So let me go ahead and do that, continue this integral here. So this is one of those rare occasions when, let's see, we got 3, we got log base 3 of u, and then a du. So what I'm trying to say is this is one of those rare occasions where you can literally just take the dt and rewrite it as a du. So that's often what we wish could happen, because that's the easiest situation. The easiest situation is where you can just take that dt and straight up replace it by a du. And that's what we were able to do in this problem, but you always have to check that that's a legal move before you do that. So we used algebra here to prove to ourselves that du was exactly the same as dt. So that doesn't usually happen, but sometimes it does. Okay, and then one other thing you might say is, oh wait, Travis, you forgot the 2 and the 9. Well, that's right, and I actually forgot them on purpose because I'm going to leave them as question marks, because the idea here is that the 9 and the 2, those are values for t. But I've now changed variables. I'm now integrating with respect to the variable u. And so the 2 and the 9, those apply when I'm working with t. But t is history. T is gone. So the 2 and the 9 are not appropriate anymore. And so what should go here? Well, we could take the time to figure out what goes there, but I prefer just to wait until the end and figure it out at the end. Or actually never figure it out. Just you'll see what I mean when we get there. So right now, I'm just going to leave those as question marks, and we'll continue. Okay, so now at this point, I think, okay, let's see. There's one little thing I could do here. I can use the constant multiple rule for integrals to factor out the 3. So I get 3, and then the integral from question mark to question mark of log base 3 of u du. Okay, and so now I have to evaluate this integral. And it's like, oh my gosh, how do I do that? So this is where it's helpful to remember some of your antiderivative rules. So your book mentions this formula somewhere. Oh no, it reloaded. I had it all queued up and ready to, there it is. Okay. So you've got that the antiderivative of log base a, well actually let's look at the natural log first, because that's the best logarithm. The antiderivative of natural log of x turns out to be x times the quantity natural log of x minus 1. And you kind of just have to trust me on that right now. In second semester calculus, you'll use a technique called integration by parts to see why that's true. But right now, you can just check that it works. And then there's just a slight modification of that formula if you're dealing with a general logarithm. The log base a of x is just x times the natural log of x minus 1. Oh, but then you have to divide by this little natural log of a. So, okay. So now what I can do here is I can use the fundamental theorem of calculus to say that, so the fundamental theorem of calculus says that, whoops, I was supposed to change colors. The fundamental theorem of calculus says that this integral, this definite integral, is going to be the antiderivative, which is x. Oh, sorry, it's not x though. There's no x. What am I saying? I'm integrating with respect to u. So it's going to be u divided by the natural log of 3, and then times the quantity natural log of u minus 1. And then that's going to get evaluated from at the upper and lower limits, which we said we don't know. All right, so what I just did there was I just basically used this antiderivative formula. That the fundamental theorem of calculus says if you want to evaluate a definite integral, then you find the antiderivative of that function, and then you evaluate it at the upper and lower limits. Okay, so now let's see here. I kind of ran myself out of room. But now what we can do is we have to deal with these question marks. And the way we deal with these question marks is we back substitute. Is we say, hey, wait a minute. I didn't know what the question marks were because those were the upper and lower limits for u. But I do know what the upper and lower limits are for t. So if I could get t back in here, then I'd be all set. And you can use this equation right here to get t back into the picture. So all right, so we're going to have, let me see here. I will erase this because it's taking up room that I need. So what we've got is, we've got 3 times, okay, so we said that u was equal to t plus 4. So wherever I see a u, I'm going to write t plus 4. So I'm going to have t plus 4 over the natural log of 3 multiplied by the natural log of t plus 4 minus 1. And then that gets evaluated at, and so now the t's are back. So since the t's are back, I can put the 9 and the 2 back. Because again, the 9 and the 2 had to disappear when we changed into the u language. But now that we're back to t, the 9 and the 2 can come back. And now we're basically done. Now you just plug in the numbers. So this is going to be 3 multiplied by, okay, so first I plug in 9. So I get 13 over the natural log of 3. And then multiplied by natural log of 13 minus 1. So that's what you get when you put in 9. And then now I'm going to subtract what I get when I put in 2. So when I put 2 in for t, I get 6 over the natural log of 3 times the quantity natural log of 6 minus 1. And that is it. That, I mean, it's not the prettiest answer in the world, but that is 100% correct. So let's go back to the original problem. That original problem, nope, that's not it. It was this one, the distance traveled. The total distance traveled by the particle is equal to this complicated expression.